Hello and welcome to the second lecture in beams. In this lecture, we will look at developing a systematic approach to finding the axial force, shear force and bending moments and their diagrams. It's really essential that we know how to do this correctly because this will form the basis for the design process in structural engineering. So let's get to it. Before analysing any beam, we must define the sign conventions used for internal forces. Three internal actions exist in beams: axial forces, which we note with N, shear forces S, and bending moments M. In structural analysis, we assign positive and negative directions to these quantities, so the results are consistent. Axial tension is taken as positive, while compression is negative. And bending moments are positive when they produce sagging, meaning the beam bends so that the bottom fibres are in tension. Beam analysis follows a clear sequence of steps. First, we define the loading support conditions on a clear structural sketch. Second, we calculate the support reactions using equilibrium equations. Third, we determine the axial force distribution along the beam and we construct the axial force diagram. Then, we determine the shear force distribution along the beam and construct the shear force diagram. And finally, we determine the bending moment distribution and construct the bending moment diagram. These diagrams provide a complete description of how the beam responds internally to loading. Different types of supports provide different constraints to the beam. A fixed support prevents both translation and rotation. It therefore provides a horizontal force, a vertical force, and a moment reaction. A pin support on rollers only prevents vertical movement, so it provides one reaction force. And a pin support prevents both horizontal and vertical movement, but allows rotation, so it provides two reaction forces, but no moment. And now that we've discussed the approach, let's begin with example 1, which considers a simply supported beam carrying two concentrated loads. The beam span is divided into equal segments and two loads are applied along the beam. Our goal is to determine the support reactions, the axial force, the shear force, and the bending moment diagrams. The first step in beam analysis is to determine the support reactions. We have a pin support at A, so that gives two reactions, AX and AY, and at B we have a roller support, so one reaction, and in this case it's in the vertical direction, so BY. We begin by applying the moment equilibrium equation. Taking moments around the left support A allows us to eliminate the reaction at A and solve directly for the reaction at B. By summing the moments of all forces around point A and setting the result equal to 0, we can determine the unknown reaction. In our case, By gives us a positive moment with a distance of 9 meters. The force of 60 kilonewtons gives a negative moment with a distance to A of 6 meters. And finally, the 120 kilonewtons also gives a negative moment with a distance of 3 meters. Isolating By and dividing by 9 gives us the value for By, which works out as 80 kilonewtons. Next, we apply the vertical force equilibrium equation. The sum of all vertical forces acting on the beam must equal 0, and in our case, AY plus BY minus 120 minus 60 must equal 0. Since we've already found By, we can now calculate AY. And this works out as 100 kilonewtons. This allowed us to determine the remaining reaction once one reaction was already found. And as a verification step, we can check our results by taking moments around the opposite support at point B. If the equilibrium equations are satisfied, the calculated reactions are correct. Performing this check is good engineering practice because it helps detect calculation errors early. Axial force occurs when forces act along the axis of the beam. In this type of internal force, it'll cause the beam to either stretch in tension or shorten in compression. By convention, tension is positive, compression is negative. In many beam problems, axial force may be 0 unless horizontal forces are present. Now we begin determining the internal actions within the beam, starting with the axial force. To do this, we imagine making a cut at a section of the beam and isolating one side of that section. At this stage, we're only introducing the axial force component, which we note as N. It's important to note that because we've not yet included the shear force and the bending moment at the cut, the beam segment is not fully in equilibrium. This diagram therefore only illustrates the axial force component, and additional internal actions are introduced in the next steps to fully balance the section. In this example, there are no horizontal loads, so the axial force throughout the beam remains zero. We can now introduce the shear force component, noted with S. Shear force results from unbalanced vertical forces acting across a beam section. Physically, shear represents the tendency of one portion of the beam to slide vertically relative to the other portion. Our sign convention defines positive shear as a force that causes the left part of the beam to rotate clockwise. Understanding this convention is essential because it determines the direction of the shear force diagram. We now begin calculating the shear force along the beam. To determine the shear at any location, we imagine cutting the beam at that point and summing the vertical forces acting on one side of the cut. Starting at the left end of the beam, the shear force is initially zero. As soon as we pass the reaction at support A, which is 100 kilonewtons upwards, the shear force increases to plus 100 kilonewtons. When we pass the 120 kilonewton downward load, the shear force decreases by 120 kilonewtons, giving us 100 minus 120, which equals minus 20 kilonewtons. Finally, when we pass the 60 kilonewton downward load, the shear decreases again. Minus 20 minus 60 gives us minus 80 kilonewtons. And at the final support, the reaction of 80 kilonewtons upwards brings the shear force back to zero, which confirms global equilibrium. A useful way to visualize shear force calculations is the cover method. We imagine covering the beam with a sheet of paper and slowly sliding it from left to right, revealing the beam progressively. At each position, we sum the vertical forces acting on the exposed portion of the beam. This running total gives the shear force at that point. Shear starts at 0 kilonewtons. Passing a 100 kilonewton reaction, the shear becomes plus 100. Passing the 120 load, the shear becomes minus 20. Passing the 60 kilonewton load, the shear becomes minus 80. And passing the final 80 kilonewton reaction, the shear returns to 0 kilonewtons. This step-by-step approach makes it easier to construct the shear force diagram. Using the calculated shear values, we can now construct the shear force diagram, or SFD. Between concentrated loads, the shear force remains constant, so the diagram is drawn as horizontal lines. At each load or reaction, the shear force changes instantly, which appears as a vertical jump in the diagram. The diagram begins and ends at 0, confirming that the beam is overall in equilibrium. Next, we consider the bending moment, notated by M. The bending moment represents the internal moment that resists rotation caused by external loads. We can visualize this by imagining the beam cut at a particular section. The portion of the beam on one side of the cut applies a moment to maintain equilibrium. This internal moment is the bending moment at that section, and it is balanced by the internal moment of the section that we just cut on the opposite side. To determine the bending moment at any point, we again consider a section of the beam and calculate the moments of the forces acting on one side of the cut. The bending moment is calculated using the relationship moment equals force multiplied by distance. We'll use the same cover method as before, but instead of summing forces, we sum moments about the section cut. Starting from the left support, the bending moment is 0. Although a force acts at the support, the distance to the section is 0, so the moment is also 0. As we move along the beam, the distance from the reaction increases, causing the bending moment to increase linearly. Now we move to the position of the first applied load, which is the 120 kilonewtons, located at 3 meters from support A. To determine the bending moment at this point, we take moments around the cut section. At this location, the only force contributing to the bending moment is the reaction at A, which we previously determined as 100 kilonewtons. The bending moment is calculated using moment equals force times distance. So here we have 100 kilonewtons multiplied by 3, which gives us a bending moment of 300 kilonewtons. Because the reaction at A causes the beam to sag, the moment is positive according to our sign convention. So, at the position of the first load, the bending moment is plus 300 kilonewton meters. This value will form one of the key points in the bending moment diagram. Next, we move to the second load, which is located at 6 meters from support A. The bending at this section is obtained by summing the moments of the forces acting to the left of the section. The reaction at A, 100, with a lever arm of 6, produces a positive moment, and the 120 kilonewtons with a 3-meter lever arm produces a negative moment. Combining the contributions gives us a bending moment of 240 kilonewton meters, which is still positive, indicating that we're still in sagging bending. And finally, we evaluate the bending moment at support B, located 9 meters from support A. Taking moments of the forces to the left of the section, we have 100 kilonewtons reaction at A acting with a distance of 9 meters, 120 load acting with a distance of 6, and a 60 kilonewton load acting with a distance of 3 meters. Summing up the moments gives us a bending moment of 0, and this confirms the expected result since a simple support cannot resist bending moment. When drawing the bending moment diagram, we follow the convention that the diagram is drawn on the tension side of the beam. To identify which side is in tension, it helps to think about what bending does to the beam fibers. One side of the beam is being pulled, which means that the material fibers are getting longer. This is tension. The opposite side of the beam is being pushed, which means that the fibers are getting shorter. This is compression. In sagging bending, the beam curves downwards. The bottom fibers are being pulled, they get longer, and therefore are in tension. At the same time, the top fibers are being pushed, meaning they shorten and are in compression. Because the bending moment diagram is drawn on the tension side, the positive sagging moments are drawn below the beam. If the bending were reversed, the top fibers would be pulled into tension and the bottom fibers pushed into compression, and then we would draw the bending moment above the beam. In this example, the moments are positive, so the beam is sagging, meaning tension occurs at the bottom and the bending moment diagram is drawn below the beam. We can now bring together the results of the analysis. At the top, we have the shear force diagram, which shows the step changes caused by the reactions and the two concentrated loads. The shear force begins at plus 100 kilonewtons at support A, drops to minus 20 kilonewtons when the 120 kilonewton load occurs, then decreases to minus 80 at the 60 kilonewton load, and finally it returns to 0 at support B. Below that, we have the bending moment diagram, which is drawn on the tension side of the beam. The bending moment starts at 0 at support A, reaches 300 kilonewton meters at the first load, reduces to 240 kilonewton meters at the second load, and returns to 0 at support B. These diagrams summarize the internal force behavior of the beam under the applied loading. We'll move on to another example, which introduces a slightly different loading case. The beam is again simply supported, but it now carries two different types of loading. First, we have a concentrated point load of 120 kilonewtons, and then there is a uniformly distributed load of 30 kilonewton per meters, which acts over part of the beam. The presence of a distributed load will change the way the shear force and bending moment diagrams behave, which we will see shortly. As before, the first step is to determine the support reactions. Support A is a pin giving reactions AX and AY, while support B is a roller giving the vertical reaction BY. Since there are no horizontal loads, the horizontal reaction AX will be 0, so we'll focus on the vertical reactions. To determine BY, we'll take moments around support A. The 120 kilonewton load acts at a distance of 3 meters, producing a negative moment. The uniformly distributed load acts over 2 meters, so first we need to find the equivalent resultant force. The resultant of a UDL is the load intensity multiplied by its length, or the area of the shape of the load, and this gives us a force of 60 kilonewtons. This resultant force acts at the centre of the distributed load, which is 1 meter from the start of the UDL. We need to take that into consideration and add on the further distance to A. Taking moments around A allows us to determine the value of BY, which works out as 80 kilonewtons. Once BY has been determined, we can use the vertical equilibrium equation to find the remaining reaction AY. The sum of all vertical forces acting on the beam must equal 0, so the upward reactions must balance the downward loads, which consist of a 120 kilonewton point load and the 60 kilonewton equivalent load from the UDL. Solving this equation gives us the value of the reaction at support A. And as before, we can verify the reactions by taking moments around support B. If the equilibrium equations are satisfied, the calculated reactions will produce a balanced moment equation, confirming the correctness of the results. Performing this check is good engineering practice. We can now begin the internal force analysis for example 2, starting again with the axial force. If we inspect different sections of the beam, we can see that there is still no horizontal loading present. So regardless of where the cut is taken, the axial force remains zero. This means that axial action does not contribute to the internal response in this example. We can now move on, therefore, to the more significant internal actions for the beam, shear and bending. Let's look at the shear, the out-of-balance vertical forces acting on the beam. If we look at the shear force in different regions of the beam, starting from the left, we can see that once we pass the reaction at A, the shear jumps to the value of the reaction. At the 120 kilonewton point load, the shear drops suddenly by 120 kilonewtons because a concentrated load causes an instantaneous change in shear. Once we enter the region of the UDL, or the uniformly distributed load, the behaviour changes. A UDL does not cause a jump. Instead, it causes the shear to change gradually because the load is spread continuously along the beam. So under the UDL, the shear force varies linearly. The same cover-up method can be used here. We cover the beam and slide the paper gradually from left to right, summing all the exposed vertical forces and taking downwards as positive in this method. We begin at 0, and then the reaction at A changes the shear to 100 kilonewtons. The 120 kilonewton point load changes the shear to minus 20 kilonewtons. Then, under the 30 kilonewton per meter UDL, the shear reduces progressively. After 1 meter of UDL, the shear changes from minus 20 to minus 50. And after 2 meters, it reduces further to minus 80 kilonewtons. It then remains at minus 80 kilonewtons until the reaction at B brings it back to 0. This is the key difference introduced by a distributed load. The shear changes at a constant rate rather than by a sudden jump. We can now draw the shear force diagram. From the left support to the point load, the shear is constant at positive 100 kilonewtons. At the point load, it drops vertically to minus 20. Under the UDL, the diagram becomes a sloping straight line, falling to minus 80 kilonewton at the end of the loaded region. It then remains constant until support B, where the final reaction returns the shear to 0. So in the shear force diagram, point loads cause jumps, UDLs cause a linear variation. Let's quickly summarize the rules that we've observed for shear force diagrams. Shear force is 0 at the ends of the beams. It doesn't change where there is no loading, so the diagram is horizontal in unloaded regions. Under uniformly distributed load, it changes linearly, and the rate of change of shear is equal to the load intensity. These are some useful rules to remember when you're sketching the shear force diagrams quickly. We'll use the same cover-up idea, taking moments around the edge of the paper or around the cut section. This allows us to build up the bending moment diagram point by point. We begin the bending moment calculation at the start of the beam at support A. At this location, the bending moment is 0. Although a reaction force acts at the support, the distance to the section is 0, so the moment, which is force multiplied by distance, is also 0. This is typical for simply supported beams where the supports cannot resist bending moments, and this provides the first point for constructing the diagram. We now move away from the support and consider a section further along the beam. As we move to the right, the distance from the reaction at A increases, so the bending moment produced by that reaction also increases. Since there's no distributed load acting yet, the bending moment in this region varies linearly with distance, and this means the bending moment diagram will be a straight line between the support and the next point where loading changes. We now reach the start of the uniformly distributed load. Up until this point, the bending moment is determined by the reaction at A and the 120 kilonewton point load. To find the bending moment here, we take moments of these forces around the section using the appropriate distances. This gives us another key ordinate for the bending moment diagram just before the distributed load begins. Next, we move to the end of the UDL region. At this stage, the effect of the distributed load must be included. A uniformly distributed load can be replaced with an equivalent resultant force equal to the load intensity multiplied by the length of the load, acting at the center of the loaded region. When we include this force in the moment calculation, we obtain the bending moment at the end of the distributed load. Because the loading is distributed, the bending moment diagram in this region becomes curved rather than straight. And finally, we move to the right support, which is the end of the beam. As with the left support, the bending moment here is 0 because a simple support cannot resist bending moment. And this provides the final point needed to complete the bending moment diagram. This slide summarises the shear force and bending moment diagrams for the beam. From equilibrium, we determined the support reactions of 100 kilonewtons at A and 80 kilonewtons at B, and using these we constructed the diagrams. The 120 kilonewton point load produced a sudden drop in shear, and the 30 kilonewton per meter distributed load caused the linear variation, as we can see in the shear diagram. Using the key values of bending moment that we calculated at significant points along the beam, we can sketch the bending moment diagram. We can see that between concentrated loads, the moment varies linearly, producing the straight segments of the diagram. However, in the region where the uniformly distributed load acts, the moment varies parabolically. This gives us a curved portion as shown here. Finally, the bending moment diagram is drawn on the tension side of the beam, which for this sagging beam is below the beam axis. Let's finish by summarising some useful rules for interpreting bending moment diagrams. The bending moment is 0 at free ends. The maximum or minimum bending moment occurs when the shear force diagram crosses 0. Between point loads, the bending moment diagram is straight, and under uniformly distributed loads, the bending moment diagram becomes curved. Another useful visualization is that the bending moment diagram takes a shape similar to a cable carrying the same loading as the beam. Thank you for joining me. I hope you join me next time when we look in a bit more detail at developing the equations for the axial force, shear force, and bending moment, as this will have a lot of uses as we go forward in our journey into structural engineering.